Assalamualaikum warahmatullahi ta'ala wabarakatuh. A warm welcome to all of you to the second distinguished lecture series. This program is brought to you live from Faculty of Engineering, Universiti Teknologi Malaysia. For your information, the distinguished lecture series is a talk platform for prominent professors, scientists, and researchers from all over the world to disseminate knowledge, to share expertise and experience, and perhaps to exchange ideas. You are with me, Mazlan Abdullah, anchoring our second lecture in this distinguished lecture series. Today, we are very much honored to have Professor Choon Ng, the Professor of Environmental Science and Engineering, King Abdullah University of Science and Technology, Saudi Arabia. Welcome, Prof. Professor Choon Ng will talk on a topic entitled Thermodynamic Framework for Evaluating the Energy Efficacy of Diverse Seawater Desalination Plants. Without further ado, I would like to invite the Dean, Faculty of Engineering, Universiti Teknologi Malaysia, Professor Dr. Rafiq Abdul Qadir, to introduce our speaker today. Over to you, Prof.
Thank you very much, Mazlan. Assalamualaikum and hello. Welcome everyone and welcome to UTM Engineering Distinguished Lecture Series, our second lecture in the series. My name is Muhammad Rafiq and I am the Dean of Engineering, Universiti Teknologi Malaysia. Today it is my utmost pleasure to welcome Prof. Choon Ng to our program.
Good afternoon.
Professor Choon Ng obtained his BSc and PhD from the Strathclyde University, Glasgow, UK in 1975 and 1980 respectively. Worked briefly at Babcock Power Limited and joined the Mechanical Engineering Department of NUS in 1981. After 34 years at NUS, he joined the Water Desalination and Reuse Center of the King Abdullah University of Science and Technology, Saudi Arabia, as a full-time faculty. His research interests are in adsorption cooling, innovative air conditioning and dehumidifier systems, seawater desalination, cogeneration power systems analysis, and harnessing sunlight to liquid fuels by CPV systems. He is keen reader of energy efficiency and its thermodynamics relation to unit cost of resource. He pioneered the use of the heat-driven AD cycle to lower the bottom brine temperature limit of MED processes. Choon is the lead PI for KAUST cooling initiative that will develop chillers for air conditioning without compressors or the use of chemical refrigerants. He has over 300 peer-reviewed journals and conference publications. He is active in professional services, serving as associate editors in 3 international journals, as well as in the Committee for PE Examination of the PE Board, Singapore. He has been on visiting professorship to the world-class university program of Jeju National University, Korea from 2008 to 2013, and also as a visiting imperial professor to Kyushu University in Japan. He has published 3 books, 12 book chapters, 14 patents, started 3 spin-off companies with licenses from NUS and KAUST. His H-index factor is 58. Total Google Scholar citations in publication is 10,867. So without further ado, I call upon Prof. Choon Ng. Over to you, Prof.
Good afternoon. Thank you, Professor Rafiq and Professor Malan for inviting me to this lecture series. It's an honor for me to speak at this second lecture speakers, as a second lecture speakers. Now, this morning or this afternoon, I shall share with you the thermodynamic framework for evaluating the energy efficacy of diverse seawater desalination plants. Now, before I start going into the details of this thermodynamic framework, I want to say a few words about the global water scenario. As you can see from here, the global water demand gap between supply and demand is startling at 40% by the year 2030. Currently, the withdrawals for potable water is about 4,500 billion meter cube per year, but the existing sustainable water supply could only supply at 4,200 billion meter cube per year. So there's a shortage gap between supply and demand. So obviously the correct problem solution is to conduct desalination to meet the future water demands. In terms of GCC scenario, the water availability in many countries are very low, typically less than the UN defined water scarcity level of 500 meter cube per capita per year. For example, Saudi Arabia, UAE, Kuwait, they are all less than 90 meter cube per capita from natural sustainable resources. So therefore, water desalination is very important for these GCC and North African countries. And as such, there is many large plants are being built for providing water to these countries. Now, this is a global water stress level for the world with an indicator in color. As you can see, the red colors represent the highest water stress indicator, and Middle East and North African countries are obviously indicated in red. And it's interesting to see that South Africa, even Cape Town, for the last 4 to 5 years, they have been running shortage of water. So you can see water is very significantly low for some of these countries, especially in west part of USA, eastern part of Australia, and parts of South America. Now, within the GCC countries, the availability of water is very low in the red boxes. You can see that it has shrunk greatly from 1962 to 2007. So obviously, the most viable option for filling this water shortage gap is by seawater desalination. Now you can see the typical diverse desalination processes or methods available in the Kingdom of Saudi Arabia. You have seawater RO plants on the left, typically supplying 192,000 meter cube per day. You have the MED plant, the experimental plant at Yambu, supplying 68,000 meter cube per day, and a very large multi-stage flashing plants, which is a thermally driven desalination plant in the coast of Red Sea. And you see that all these plants have their specific energy consumption expressed in terms of the secondary or derived energy, such as electricity and thermal input. Now, this electricity is given in terms of kilowatt hour. So you can see that for RO is between 3.2 to 5.5 kilowatt hour electric per meter cube. For thermally driven plants like MED or MSF, they are given by both electricity and thermal input. For MED, the thermal input is about 2 kilowatt hour electric per meter cube, but the thermal input is given as 60 to 70 kilowatt hour per meter cube, and slightly higher values for multi-stage desalinations. So the question come to your mind is probably, which are these processes is the most efficient? And the second question you have to ask yourself is, are the derived energy units like kilowatt hour is sufficient unit for comparing energy efficiency? So it is in this talk that I want to let you know how presently there is some misconception about the energy units currently being used in the industry. Now, before I go into the details, let me share with you some basic facts. Now, energy efficiency is not a law of thermodynamics like second law, first law, and so on. It is merely a figure of merit describing the ratio of useful output to the energy input you get put in to get that useful output. So it is, as long as the figure of merit is acceptable to the user, then energy efficiency is used for comparing the efficacy of the processes. As you know, all the secondary energy or derived energy comes from converting primary energy in power plants. And because of the disproportionate destruction of the available work or exergy from this primary energy, they are created not equal. Therefore, the implicit assumption, parity assumption of 1 kilowatt hour electricity, same as 1 kilowatt thermal, may cause serious misconception. And it has, unfortunately, with us for the past few decades. Insufficient correct way of defining efficiency may lead to an inferior decision on the selection of desalination plants for our economy to be deployed. So therefore, the purpose of this talk is we are proposing a thermodynamic framework to capture the absolute values of the secondary energy so that we can compare it using a common energy platform, as we can see later. Now, to highlight the differences in the quality and the quantity of energy, I've used some very simple thermodynamics expressed in the Carnot cycle. Here you can see on the upper chart, 3 Carnot cycles, but they are all supplied with the same quantity of energy, 1 kilowatt hour, for example, which is equal to 3.6 megajoules. As you can see, on the left-hand side, that cycle is supplied at a high temperature reservoir temperature at T1, and the blue rectangle represents the available work, while the red rectangle below represents the unavailable work. And as the heat supply comes at a lower temperature, lower heat source temperature, as shown in the middle figure, you can see that the available work is diminishing. And to the extreme, when you supply the same quantity of heat at a temperature slightly above the ambient, T0, you can see that the amount of available work is negligible. Therefore, the energy units kilowatt hour per se may not be sufficient to describe the absolute value of the energy that is supplied to run the process. So all processes, whether it's work-driven or heat-driven, can be represented by the simple cartoons you see at the second left picture. The first picture represents an engine where it draws heat from a high temperature reservoir TH1, rejecting to a lower temperature at TL1, at the same time producing maximum work we call the Carnot work as WC1. In the heat-driven process engine, we call it the reverse engine, all the processes are reversed with work being put in to run the process cycle and deliver useful product in that cycle. And all these engines would follow the second law of thermodynamics. What I've shown there is a corollary of the second law, where WC over the temperature difference ratio between the high reservoir and the low temperature reservoir is equal to QH over TH, is also equal to QL over TL. Anybody familiar with basic thermodynamics can easily derive this equation. Now, just to recap that the existing method of evaluating energy efficiency is from the secondary energy like electricity to the useful product, which is water, that you desalinate from the impaired water, or the supply of steam, thermal energy, to the thermally driven processes, also to produce water. So they are given as what I shown earlier in kilowatt electric per meter cube or kilowatt thermal per meter cube. Now, in this manner, you cannot see the full picture. In fact, we should be looking back as far as the burning of the primary energy on the left through a conversion power plant, such as the CCGT power plant. Currently, the best available power plant in the world is the combined cycle gas turbine power plant. You can notice that primary energy like natural gas is first burned in the combustor of gas turbine plant, and it consumes more than 60% of this fuel exergy just within the gas turbine plant. And the rest of 30% is then used in the heat recovery steam generator that produces the steam to run the steam turbines. Only a fraction of the thermal energy is then bled to run the thermally driven desalination processes. So in this manner, so when you come back to this picture, you can see that if the current units of kilowatt hour electric is not the same as kilowatt hour thermal, then we are not actually comparing apple with apple. Rather, we are comparing dissimilar energy quantities. Therefore, just to remind everyone that energy is created not equal in the combustion plant. So a possible design for a good desalination system would be as shown in this pictorial view, where the CCGT take the primary energy source from LNG tanker or pipelines, which then run in a CCGT, producing electricity and thermal steam to run the three existing practical methods of desalination, such as SWRO, MED, or MSF. Now, when you go look into details of the CCGT, you can see that the cycles in CCGT can be shown in this temperature cascade manner. The fuel that burns at TH1 in the combustor runs the gas turbine and rejects to a lower temperature reservoir represented by the HRSG, that is the heat recovery steam generator. At the same time, it produces maximum work WC from the gas turbine. And that heat source is then recovered to run the steam turbine at the cycle below, which at the same time produces electricity with a maximum work of WC from steam turbine. Only a fraction of the steam is bled off as QH3 at a very low temperature and pressure to run the thermally driven desalination plant. So for these cascaded cycles, we can decompose the CCGT cycles into a common platform, which we use the adiabatic flame temperature of the input fuel to represent the heat source, the highest heat source temperature that a fuel can provide when the fuel is burned in excess air in the combustor. So the key point here is to keep the Carnot cycle work so that it can represent the gas turbine in this decomposed cycle. So as you can see, with the gas turbine having the same work output, then we can compute for the corresponding energy that is supplied from this high temperature reservoir at QSPE. SPE stands for standard primary energy. We call this standard because this is the highest temperature difference one could have in a CCGTs that burn a particular fuel. And all the energy is then rejected to the ambient. And the same can be said for the steam turbine. And again, we keep the characteristic work from the steam turbine to be the same. And similarly for the desalination plant. So with this technique, we can decompose the complex processes, which is operating in cascade, into three separate individual cycles, where each drawing a separate amount of QSPE depending on the amount of Carnot work the original cycle can produce. When you add up all the QSPE, it will sum exactly to the calorific value of the fuel input. And this is the way we check whether the technique is on the right path or not. So coming back to the equation of second law, which is given in equation 1, we can then derive the conversion factor for the convenience of the engineers to convert currently the kilowatt electric into the QSPE that is set at the same as a common temperature platform or energy platform. And you can see that for work-driven processes, the WA is found in the denominator because the Carnot work can be expressed in terms of WA with the second law efficiency. And similarly, for the heat-driven process, the actual heat that is supplied to the top brine of the MED is the QA in the denominator. So with the adiabatic flame temperature taken to be 1750 Kelvin and the ambient at 30 degrees Celsius, this temperature ratio platform is worked out to be 0.8268. And this is another expression, another way of writing the conversion factor for electricity with respect to the QSPE. It can be expressed as seen at the right-hand side in terms of both the temperature platform and the second law efficiency, which is defined as WA over WC. And given the standard condition in the CCGT with the common platform as a fraction of 0.8268, a second law efficiency of 61%, that conversion factor for electricity works out to be 1.9787. Bear in mind that the electricity comes from two turbines, gas turbine and steam turbine. Therefore, you have to do the weighted approach to get the combined value. So from this conversion factor, it implies that 1 kilowatt hour of SPE, that means the energy that is drawn at the standard adiabatic flame temperature to run the engine for producing electricity, you can only get at the best about 0.505 kilowatt hour electric. In other words, all the other losses found in the engines, such as the combustion losses, the windage losses in the gas turbine, the work done in the compressors, the friction losses, occupies the other 50%. In the same manner, the conversion factor for a multi-stage heat-driven process can also be expressed in terms of a conversion factor for the ease of engineer to convert the existing thermal energy that consumed by these processes into QSPE, the energy that is drawn at the common platform. So when we work backward, you see that the conversion factor for thermal is very minute at about 2.37%, 0.0237. In other words, 1 kilowatt hour of standard primary energy is equivalent to 42 kilowatt hour of thermal measured at very low temperature and pressure of 70 degrees Celsius and less than 1 bar. So in other words, this latter quantity, the thermal energy that we use to run thermal processes, is a very low-grade energy as compared with the standard primary energy. So we can also compare the conventional approach in the table on the right-hand side, where we do the conventional approach, that means using energetic approach, where the parity between kilowatt-hour electric and kilowatt-hour thermal are set as the same. Their proportions of energy usage is given as 43% for the gas turbine, for the steam turbine about 39.58%, desalination is about 11%, exhaust flue gas that is coming out of the gas turbine, and the condenser, steam condensing in the condenser is about 5.5%. But with the thermodynamic approach, where we use a common platform for the energy drawing at the adiabatic flame temperature, the exergy destruction can be given by 57% for the gas turbine, 40% also for the steam turbine, but merely 1% for thermal desalination, because the heat that you draw for thermal desalination is of very low quality. And the energy that you throw out with respect to the QSP is only 2% at the flue gas and the condenser. So with this, we analyze a typical CCGT consuming about 2,000 megawatt of calorific fuel energy of natural gas, and run through sets of gas turbine, steam turbine, MED, and eventually exhaust plus the condenser. You can see in the blue bar in this chart, by the way, the y-axis is in the log scale. So the blue bar represents the amount of megawatt at the supply at the equivalent adiabatic flame temperature, which is 1147 for the gas turbine, 799 for the steam turbine. Only 5.8 is needed for the MED, and the losses in the exhaust and condensers are at 47%. And you can see when you sum up all the standard primary energy, it comes to about 2001. The slight error there is due to computational accuracy. The derived energy, that is whether it's electricity or steam, is given in the respective color of brown and green. So the brown bar represents the electricity of the gas turbine, the electricity produced by the steam turbine, and the thermal energy that is consumed by the top brine stage of the MED is shown in green. Of course, for the last exhaust, there's no useful effect. So based on this, we can calculate the weighted conversion factor as 1.9787, just based on these values of QSPE over the actual derived energy. So with these conversion factors, we can then convert the existing method of specifying specific energy consumption in terms of kilowatt electric into standard primary energy. For example, for SWRO with a specific energy consumption of 3.54 kilowatt electric per meter cube, when you multiply by the conversion factor needed to transform itself to the common energy platform at the adiabatic flame temperature, that is equal to 7 kilowatt SPE per meter cube. For the heat-driven process like MED, where the electricity consumption in the conventional manner is 2.0 kilowatt electric, and the thermal heat supplied to the top brine stage is 70 kilowatt hour thermal per meter cube. And when we multiply by their respective conversion factors, you can see that the sum of all the energies now in standard primary energy is 5.61. Now you can add the two together, even though they are different forms of derived energy, because we have normalized back to the standard primary energy. And just in the same tradition of efficiency definition, which is usually defined as a useful product over the energy input, so we can invert the standard primary energy per meter cube to meter cube per kilowatt hour of standard primary energy. In other words, for SWRO, it will be 0.143 meter cube for the consumption of 1 kilowatt hour of standard primary energy, whereas for the MED is 0.178 meter cube for 1 kilowatt hour of standard primary energy. Now although there are slight more efficient in MED, but we are still very far from the thermodynamic limit. As you know, thermodynamic limit is calculated independent of the process at 0.78 kilowatt hour standard primary energy per meter cube. Sorry, there's a typo there, per meter cube. And when you convert to the standard way of output over input, at thermodynamic limit, that water production is about 1.28 meter cube per kilowatt hour standard primary energy. So we went back to the literature, looking at all the specific energy consumptions of the performance of all the desalination plant from 1983 to the recent years, 2017, about 60 plants. And when we plot this conventional way of defining output over input, the output is meter cube of water, input is kilowatt hour, but now everything normalized to standard primary energy, we can see that all the existing methods, whether it's SWRO, MED, or MFSF, they are all fairly inefficient. They are merely 10 to 14% of the thermodynamic limit, which is at 1.282 meter cube per kilowatt hour. We believe that based on design experience of engineers and scientists, we can reach a sustainable level of about 35 to 40% of the ideal limit in many engines that we've seen, like internal combustion engines, gas turbine, and so on. Yet, the current desalination processes that we have are very low energy efficiency. So there's much room for improvement. So at COWS, we work on hybrid thermal desalination. That means we combine the proven MED with another thermally driven absorption desalination cycle. We call it MED plus AD, or MEDAD, MED-DAD in short. In the laboratory, we have tested that this hybrid desalination can achieve 0.354 meter cube per kilowatt hour of standard primary energy. And the next slide shows our experimental pilots in COWS. So in 2013, we built the absorption desalination pilot plant, which is solar driven. The tanks with the yellow railing at the top are the solar hot water storage tank, where solar energy is stored in the hot water and then is used to run the AD plant on the bottom of the figure. And in the year 2015, we designed the 4-stage MED plant to be linked to the AD plant below the mezzanine floor. The mezzanine floor is putting above the AD plant, and the two vapor pipe that you see curved down goes to link to the beds of the AD absorber. And this plant was commissioned in 2016. And you can see my research scientist formerly, now he has went to UK as an assistant professor at Northumbria, Professor Muhammad Wakil Sarshaza. He is in the foreground together with me. And when we run the processes pilot in Cowes and in Singapore, the picture on the left is the one running at Cowes in 2016. So by MED alone, you can see that all the temperatures are from 55 to about 39 degrees Celsius, the four-stage temperature. The minute we combine the MED with the AD cycle, you can see that the AD adsorber with the adsorbent silica gel able to pull down the last stage temperature of the MED to nearly 10 degrees Celsius. And that increases the delta T for every stage and hence boosts the water production. And the HMI chart below shows the water production for MED at 2.1 liters per minute. And when it's run as a hybrid cycle, it boosted the water production to about 4 liters per minute. And the same is also found in our earlier plant at Singapore, at NUS, where Dr. Wakil did his PhD. You can see that there is a water production boost when you run in a hybrid operation, MED-AD operation. So you can see that the green represents the MED operation alone, and there's a limit to the temperature because you cannot go down below 40 degrees Celsius because due to the high ambient in the Middle East. And but for the MED-AD, we are able to lower this temperature limits to as low as 15 degrees, as shown in the red dots, showing the boost in water production. Thereby, it improves the efficiency up to 25 to 28% of the thermodynamic limit indicated by the star point, which we presented in a recent paper at Desalination. So in conclusion, I would like to conclude that currently all existing desalination processes in the large-scale plants are running merely less than 18% of the ideal limit, and there is yet further room for improvement in designing desalination processes. And we have demonstrated a hybrid thermal cycle called the BDAT cycle, where we are able to achieve 25%. And also I have presented a common energy platform to capture the absolute value of the derived energy that is supplied at varied temperature conditions. Some electricity is a very high-grade energy, while thermal heat at 60, 70 degrees Celsius is a very low-grade energy. So with that common platform, we are able to meaningfully present the energy efficacy of all existing desalination plants on a common energy platform. The caveat here is the conversion factor that is derived is based on the best available power plants that is currently available, that is the CCGT. Should there be further improvements in the power plants that may include green electricity from renewable solar, wind or hydro, or even blue energy, what we call the blue energy is the osmotic power generation from PRO, then this conversion factor can be easily adjusted to take into account of the contribution of this secondary energy as a feed and as a convenient energy for running all the diverse desalination plants. So with this note, I thank you for listening. Maslan?
Thank you very much, Professor. That was a very informative and a very interesting talk. So we hope your talk has shed some light to all of our viewers. Now we would like to take few questions from our viewers. Okay, the first question from Dr. Muhammad Fairuz Muhammad Yassin. Thanks for the information talk, Prof. Ng. What do you mean by efficiency is not thermodynamics law?
That is a very good question. Thermodynamics law, as we have studied, is merely first law and second law. Efficiency is a figure of merit, output to input. It's a ratio of useful output. In desalination, that would be meter cube of water. And input is the energy that you put in the denominator. The ratio of these two parameters gives you a kind of figure of merit, which we call energy efficacy. And there's no laws to define as long as, in fact, there are many examples that you see. For example, they call the efficiency of chillers as COP because that number becomes greater than 1. The reason that the COP of chillers become greater than 1 is because we are converting high-grade energy into the low-grade thermal energy. So efficiency is not a law. It is some figure of merit that users accepted them. That's all. The key question here is, what is the way you define the energy? So the secondary energy like electricity and thermal heat can come at many levels, many grades: high-grade steam, intermediate-grade steam, low-pressure steam, or low-temperature steam. Those steam, although the quantity is the same kilowatt-hour, but the quality is very weak in terms of ability to produce useful work. However, it works very well in evaporation because evaporation occurs at almost constant temperature. That's why the MED, MSF, it works quite well since the 1960s. I hope I answer your question.
Thank you. All right. Okay, we're going to the second question. It's from Dr. Wakil. How about renewable energy utilization for this desalination? Can calculate CF?
That is also a very good question, Dr. Wakil. Yes, we can. Currently, I have made the assumption that all the electricity and all the thermal heat comes from CCGT. In fact, with improvement in renewable solar, the fraction of solar green electricity is increasing from year to year. Currently, we are looking at 5% to 7% of contribution of electricity from this green solar. So when this contribution becomes significant, we have to adjust the conversion factor to account for the conversion factor computation. That means we have to look at how can we incorporate the green electricity using the same common energy platform. And for that, there are a lot of interesting work being carried out where we use the photosphere's temperature of the sun as the top heat source temperature. When you have that, you can then combine all the methodology together. So I hope I answer your question.
Okay. All right. This is from Nura Muaz. Prof, if the inefficiency of CCGT plants is below 20%, then from economic perspective, can we consider it worth application?
Well, thermodynamics allows one to be non-innovative. It doesn't buy you to be wasteful, to be non-innovative. The best CCGT plant available today was reported in Japan, near to 60+%. That is the best CCGT, but there is some degree of unfairness in their reporting because their ambient at that time when they were testing is only 10 degrees Celsius. There are not too many countries with 10 degrees C ambient, except in winter season in certain countries. Many of the MENA countries, Middle East and North African countries, have ambient way above 35 degrees in summer. So CCGT plant usually operates between 50 to 60%. Only the traditional steam boiler fossil fuel plants observe the 1/3 limit about 33% limit. But with CCGT, where the fuel burn is normally single carbon atom, the methane gas, that efficiency will go ways beyond 50%. I hope I answered your question.
Okay, thank you, Prof. All right, let's go for this is question from Professor Idrus Alhamid from Indonesia. Is there is there an easy designation to describe efficiency in the desalination process?
Well, thank you, Pak Idrus, my old friend from UI. As I mentioned, efficiency is just a ratio of useful output to the energy input to get that useful output. It is not a law of thermodynamics. Therefore, the thing is, when you define the secondary energy that we are using for convenience these days, does that energy units capture the absolute value of the energy that you are supplying? That energy can come at combustors of gas turbine at 1750 Kelvin. It can come from steam after heat recovery steam generator at about 115 bar, 560 degrees Celsius. It can operate all the way down to below 45 degrees Celsius. So at what point can you tap the low-grade energy to run the desalination process? And how to evaluate that low-grade steam? The implicit assumption of 1 kilowatt hour electric to 1 kilowatt thermal, irrespective of the temperature of supply, is not a correct way. In fact, unfortunately, it has caused a lot of misconception. And therefore, you can see many countries are selecting the wrong methods for installing power plants. When a power plant is installed, it lasts for 25, 30 years. If you select the inferior process that has high maintenance cost, high capital cost, the unit cost of water going to be a burden to the people in the country for as long as the plant life of 25 to 30 years. So I hope I answer your question.
Okay, thank you for that. We go to I think one more question from Faiz Riaz. High temperature thermal energy should not be equal to low temperature thermal energy. So cannot compare KW to KW as well? Any comment, Prof?
Precisely, that's a good question. That's why we are proposing a common energy platform using the diabatic flame temperature as a high temperature source. And all engines that you can have your engines operating at different temperature levels, maybe from 560 to 200, one operating from 70 to 40. As long as the Carnot work, the maximum work according to your actual process is preserved when you normalize to the QSPE, the common platform, you are representing the same work produced by the actual process. Now, your heat transfer from that common platform represent the equivalent energy. So from system A to system B, then you can compare QSPE1 to QSPE2 when you put in the denominator of the efficiency definition. The output is the same, meter cube of water. It's only the numerator, only the denominator, that energy that you use, the kilowatt hour, has to be catered for both quantity as well as the quality of the energy. If you can have that done, you are now comparing apple with apple. Otherwise, it's not a fair comparison. Thank you.
Okay, thank you. Prof, are you ready? We have one more question if you're able to answer.
Can, sure.
Okay. All right, this is from Kian Chen. Is there any possibility to derive a more universal CF that is independent of temperature and pressure?
Now, that is the purpose of a CF. you have to fix your common platform. Under the common platform, we are fixing the temperature and pressure, in other words. So when we normalize the actual process using the Carnot work back to the platform, you are taking both quantity and quality into account. Only when you do that, you get the correct primary value of the energy that you supply to operate the process. That's why you can see for electricity, 1 kilowatt hour electricity requires 1.9787 kilowatt hour of primary energy to produce. On the other hand, 1 kilowatt hour of thermal energy at 70 or 80 degrees Celsius only requires 0.0237 kilowatt hour of the QSPE that is normalized back to the adiabatic flame temperature platform. So with that thermodynamic approach or framework, we can then unify the value of the energy that consumed by the individual processes in the actual practice. That's the purpose of these conversion factors. I hope I answered the question.
Okay, Prof, maybe one more question.
Oh, okay, yeah.
Okay, from Ye Kel. Thank you for an inspiring presentation. Can Prof comment on the stand-alone system of a work-driven RO and low-temperature desalination system from the second law of thermodynamics? Probably the entropy generation statics between these systems to reflect the thermodynamics.
This is a very good question again. Now, as I said earlier, thermodynamics does not bar you from being wasteful or non-innovative. You can even burn natural gas in an open fire and put a pot of seawater. Imagine that. And then you put a slanting plate over the steam that is coming out of your pot to get the condensation as heat is rejected. So water is condensed on the back side of the plate, and then you collect that water. Thermodynamics allow you to be as wasteful as that. You burn very valuable natural gas, methane gas, in the open fire. However, you can maximize the exergy of the fuel by designing temperature cascaded processes like the CCGT. I'm not saying CCGT alone. Designers can design other cascaded processes that maximize the exergy of the input fuel. In that sense, then an energy planner of a country should plan their electricity demand and the water demand according to the best available technology. But there are occasions you have to use RO plant in some remote places where there's no seawater. You're a few hundred kilometers from the coastline, but you have a lot of impaired wastewater or groundwater. Then RO plant works very well. There's no problem because of that situation. But if you're planning for mass production of electricity as well as water to supply to the economy of a country, then you must look for the best way of maximizing your available primary energy. So as I said earlier, thermodynamics allows you to be non-innovative. You can be extremely wasteful. But if you try to be clever or innovative, you put bounds and limits on you by the second law of thermodynamics. Thank you.
Thank you very much, Prof. I think that's no more question from the audience.
Thank you. Have a good day.
Thank you very much, Prof. Choon Ng, for your valuable time. You be able to spend time with us. That was a very intellectual and informative talk. Okay.
I want to wish everyone that lock in, stay safe and be healthy in this difficult COVID-19.
Yes, especially COVID-19 era.
Yeah.
Okay, for our viewers, we are very much grateful to have you live with us today. Thank to all of you who have joined our flagship webinar series today. We hope you enjoyed it and remember to join us again in a near future because we're going to have a series of this kind of talk very soon. Please stay tuned with us. Remember, please share, like, and comment on our Facebook page, Faculty of Engineering, UTM. Thank you again.
Thank you.
Prof. Ng, Prof. Kim Choon Ng, our deepest gratitude to you for sharing your knowledge with all of us. Thank you so very much. And to all of you watching this program throughout the globe, and we have viewers from the Middle East, the UK, Indonesia, just to name a few. Do share, like, and give comments at our Facebook, the Faculty of Engineering, Universiti Teknologi Malaysia. Do share this video to all your friends and colleagues worldwide. Thank you for watching. I'll see all of you in our next episode of UTM Engineering Distinguished Lecture Series. Bye for now.
Bye-bye.